Welcome to Units and Dimensions. So thus far, the problems that we've worked on have had one question based on one set of data. But sometimes we are asked more than one question about one set of data. And answering these types of questions will require us to make distinctions between two types of equalities that we have listed in our data. So let's take a closer look at quantities, measurements, and units. Things that can be measured are called physical quantities, often shortened to quantities or dimensions. Now we can measure physical properties using measurements based upon the fundamental quantities. In chemistry, the fundamental quantities we're concerned with are distance, mass, time, electrical charge, temperature, and amount of substance. A measurement is composed of a magnitude, this is a number, and a unit, which is a standard dimension that we use to measure with. Any system of measurements must start with some arbitrary definitions for some base units that are used to measure the fundamental quantities. So in the SI system, we have some fundamental quantities: distance, mass, time, electrical charge, temperature, and amount of substance. And the base units associated with those are meter, kilogram, second, coulomb, Kelvin, and mole. And then you can see over here the abbreviations for those units. In contrast to a fundamental quantity, a derived quantity has a definition that uses more than one fundamental quantity or uses a fundamental quantity to a power other than one. For example, speed is distance over time, volume is the cube of distance, molar mass is mass per amount of substance. That is, a derived quantity is measured in units that are a combination of more than one fundamental unit. For example, meters per second is a measurement of speed, meters cubed is a measurement of volume, and grams per mole is a molar mass. The derived quantities and units that are often used in chemistry are here. We have area, which is a distance squared. We measure that in meters squared. And then over here we've got some other commonly used units. We've got meters squared and centimeters squared. Volume is a distance cubed. We usually write that either as meters cubed or as liters or milliliters, sometimes as cubic centimeters. Speed is a distance over time. That's generally meters per second. Density is mass over volume, which is kilograms per meter cubed, or grams per centimeter cubed, or grams per milliliter. Concentration is particles per volume, which is generally moles per cubic meter, or moles per liter. Molar mass is mass per particle, so kilograms per mole, or grams per mole. Acceleration is velocity over time, which is meters per second squared. This is basically how the speed is changing with respect to time. So we're taking the speed, a change in speed, divided by some change in time. So that's the speed units divided by another time unit, so seconds. So meters over seconds divided by seconds is going to give us meters per second squared. Energy is a force times distance, and that means that now we have kilograms times meters squared divided by seconds squared, and we often use units of joules or calories to measure energies. Pressure is force over area, so we have kilograms divided by meters times seconds squared, and that is pascals or torr, or millimeters of mercury, or atmosphere. Those units are a bit more common. Frequency is the inverse of time, so 1 divided by time, and that's 1 over seconds, or hertz. So some derived units are simply abbreviations for combinations of base units. Like a liter is an abbreviation of a cubic decimeter, a milliliter is an abbreviation of a cubic centimeter. The capital M, molarity, is an abbreviation for moles per liter. An hour is simply an abbreviation for 3,600 seconds. A joule is an abbreviation for kilograms times meter squared per second squared. Now, sometimes we need to convert from a derived unit into the base units in order to solve a problem. That is, sometimes we can convert a derived unit into its base units and then cancel some of those base units with other units that are already existing in the calculation. Some of those base units are already there. In the problems we look at, there are three types of units. There are single units, ratio units, and complex units. And let's look at each one of these individually. Single units have one kind of base unit. The base unit may have a prefix like millimeters or kilometers or kilograms. It may be a multiple of a base unit, like hour is simply a multiple of seconds. It may have a positive exponent, like cubic decimeter or cubic centimeter or square meters. But if the unit on a quantity has a unit in the denominator, it is not a single unit. So ratio units have one base unit in the numerator and one of a different base unit in the denominator. That is, ratio units are a ratio of one unit per one other unit. And each of the base units involved may include prefixes and or powers. For example, kilometers per hour or grams per cubic centimeter, grams per mole or moles per liter. On the other hand, complex units have more than one base unit in the numerator and or more than one base unit in the denominator, or no unit in the numerator. That is, complex units are any unit that is not a single unit or a ratio unit. For example, joule is a complex unit because we've got kilograms times meters squared divided by seconds squared. So the fact that we have kilograms and meters in the numerator there means that joule is a complex unit. Hertz is a complex unit because now we have no units in the numerator, we just have 1 over seconds. So complex units are discussed in detail in later chapters. So physical quantities can be either intensive or extensive quantities. An extensive property is a physical property whose value is proportional to the size of the system it describes. That is, it depends upon the amount of stuff we have present. For example, mass, volume, energy, area, and distance are all examples of extensive properties. The mass of an object depends on how much stuff is there. The volume that that object takes up depends on how much stuff is there. The energy contained in the object and so on, those all depend on how much stuff is there. On the other hand, intensive properties are properties whose value do not depend upon the size of the system they describe. That is, it is independent of the amount of stuff present. So some examples here are temperature, density, molar mass, pressure, melting point, concentration, color. The color of my board doesn't depend upon the size of the board. The temperature of the board doesn't depend on how large the board is. The density of the board doesn't depend on how big the board is, and so on. Now often, if a ratio is composed of two extensive properties, then that ratio is an intensive property. For example, density is the ratio of the mass of the system to the volume of the system. And if we double the amount of a substance that we have, then we're doubling the mass, but we're also doubling the volume. And this means when we take the ratio between them, the density, that ratio is the same. So the fundamental and derived quantities are called dimensions. And the technique we've used to convert from one dimension to another, or one unit to another, is called dimensional analysis. This is the conversion factors that we've been using so far. And we can often use dimensional analysis to convert from one unit to another in such a way as to get the answer that we're looking for simply by getting the correct units. So make the flashcards listed on page 234 of the textbook and run these flashcards until they're all in your got 'em stack. So that was units and dimensions.